Thank you for kind introduction and good afternoon, everyone. I'm Kazuki Kikawada from Tokyo University of Agriculture and Technology. So today I'd like to talk titled Ionic-Liquid-Functionalized Graphene Devices for Trace Detection of Gas Molecules. So at first, let me explain the background of my research. And gas detection technology is very important for, especially in environmental monitoring, for controlling environmental issues such as air pollutions. And also it is very important for breast analysis for healthcare, especially in monitoring some kinds of biomarkers. So it is necessary for the development of highly sensitive gas sensors based on small electronic devices. So our groups focus on the graphene, and here is the structure of graphene. And this material is perfect two-dimensional structure, and this material have also high carrier mobility and chemical stabilities. And graphene is synthesized by the chemical vapor deposition (CVD) process, like here. And this picture shows the graphene on the copper foil. And this white area is the monolayer graphene synthesized on the copper foil. So many researchers have studied about graphene-based electronic devices, and our groups fabricate graphene field effect transistors, graphene FETs. And this is a structure of graphene FETs, and this is a metal electrodes called source and drain. And also the graphene is located between the drain and the source electrodes, like here. And here's the graphene FET arrays we fabricated, and this is a Japanese coins, and this is a graphene FET arrays. And here's the optical microscope image of graphene FETs. And this area is the graphene. So next, this slide shows the characteristics of typical graphene FETs. And this graph is called transfer characteristics of the graphene FETs. And horizon axis is the gate voltage prior to this device. And also the vertical axis is the drain current. And drain current is a current between the source and drain. And this minimum point is called Dirac-point, and this is a very important thing. So when negative charges were adsorbed on the graphene surface, transfer characteristics is shifted in the positive voltage direction. In other words, transfer characteristics move on the right side, and this is a mechanism of the electrical sensing using graphene devices. So this slide shows the gas detection, especially in the nitrogen dioxide detection results using pristine graphene FETs. And pristine means there are no receptors on the graphene surface. And as you can see, this is the transfer characteristics when the nitrogen dioxide were introduced into the graphene FETs from one parts per billion to the 1,000 parts per billion. And as you can see, there are many there are small shifts in the transfer characteristics. So we can we think surface modification or surface functionalization is necessary for enhance the sensitivity of graphene devices. So in this study, our groups focus on the ionic liquid, and this material is the liquid state salts composed of cations and anions. And this material have thermal and chemical stability, and also they can capture some kinds of gas molecules. And at first we fabricate the graphene FETs, and also the ionic liquid were drop cast on graphene devices as shown in this figure. And this study's purpose, this study's goal is to highly sensitive gas detection using Ionic-Liquid-Functionalized Graphene FETs. And in this study, we focus on two kinds of gas molecules, nitrogen dioxide and also trimethylamine TMA, and they are very harmful substances for our bodies, even in very low concentrations. So here is the outline of my presentations, and okay, at first, I'm going to talk about the gas response characteristics of ionic liquid functionalized graphene devices. So here is nitrogen dioxide detection results using these graphene devices. And here is the transport characteristics when the nitrogen dioxide were introduced into this device from 8 parts per billion to the 1,500 parts per billion. And as you can see, the transport characteristics shift in the positive voltage directions. So which means that this device can detect nitrogen dioxide at very low concentrations. And on the other hand, this is a trimethylamine TMA detection results, and using this device, and as you can see, the negative voltage shifts were observed in these transport characteristics. And here's a plot of the Dirac-point voltage shifts versus the each gas concentrations. And as you can see, the when the increase of the gas concentrations, Dirac-point voltage shift is increased. So next, analysis and evaluation sensing performance of ionic liquid functionalized graphene devices using Langmuir absorption as and here's the Langmuir absorption as like here. And there are two important parameters in these equations. And first is the dissociation constant KD and also the maximum voltage shift delta V max. And here is the plot of the Dirac-point shift versus gas concentrations. And here is the KD dissociation constant. And also the delta V max is from here to here. And here's the experimental data of this study. And as you can see, our experimental data were fitted by the Langmuir absorption as sum, and the KD and also delta V max were calculated to as shown in this figure. So from these results, Ionic-Liquid-Functionalized graphene devices can detect highly sensitive and quantitative gas detection from several tens of parts per billion to the sub-ppm concentration regions. So lastly, I'd like to explain the gas detection mechanism of our devices. So to investigate the mechanism of the gas detection mechanism, our group focused on the power relationship between the Dirac-point shift and carrier scattering rate, and G is equal to the transconductance of this device, and B is power law exponent like here. And here's a plot of the Dirac-point shift versus carrier scattering rate. And this graph is log scale. So this fitting line, the slope of this fitting line is equal to the power law exponent. So according to the previous studies, when B is equal to 1.2 or 1.3, it is defined as the carrier scattering, Coulomb scattering by point-like charge impurities on the graphene surface, like here. And also, when B is smaller than 1.0, it is defined as Coulomb scattering by cluster-like charge impurities, shown in this figure. So this is experimental data of this study, and the power law exponent is calculated to be 0.93 and also 0.95, which means in this case, which is b is smaller than 1.0. So from these results on the graphene and ionic liquid surface, there are cluster-like charged impurities composed of ionic liquid and gas molecules. So these charged impurities modulate the graphene's potential and induce the Dirac-point shift. So yeah, here's the conclusion of this study, and here's the funding resource. Yes, thank you for listening.
Thank you.